Yes, you're here.
Are you sure?
We did A7. I'm very sure. We're on A8.
But I have a question.
About?
The mechanics.
Yeah?
So I want to ask, this chapter is important.
Oh, yeah.
The center of gravity and principle of momentum.
Yes.
Quantity level.
Yes.
Equilibrium.
Yes. Yes.
They are important.
Yes.
I never saw this question in our exam.
Really? Why?
Or is other.
They're not in these exams, but I have seen them before. Yeah. Okay, let's continue. A8. A long straight wire carrying...
Are you sure?
What? Am I sure what? We did A7. Definitely. 100% A7. You didn't write it down?
I read everything you talked down, but now not A7.
Andy, did we do A7? Oh, that's right.
I wrote it
$1 million, I'm sure.
Yes, we did A7.
No, I don't think so. That doesn't matter. You can watch the video. Watch the video. It's there. At the end of the video. Yes? 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 Yes, yes. A long straight wire carries 6.58 amps. It's pointed so the wire is at an angle 70 to a magnetic field. So the formula for the force is BIL cos theta. And I think that... Goodness. Sorry, it's not theta. The theta is 70. So... .21 newtons, that's 8. Okay. A9. A9.
What is the B?
Oh, boo-hoo. Boo-hoo-hoo. The B, the flux density. It's given in the question. In Tesla. Oh, make me worry. Right. An electron in a vacuum is accelerated by a potential difference of 1.8 kilovolts. What's the velocity? So the potential energy here equals the kinetic energy here. So potential energy is Q QED equals a half mv squared. But the E is, if you remember the formula, is V over D. The D's cancel. So you have QV equals a half mv squared. That's voltage V now. Now, so the V velocity will be 2qv over m square root. So the velocity is square root twice the charge of an electron times the voltage, which is 1.8 kilo, all over the mass of an electron. Yep. Yes, yes. What's your question? Which formula? It's not in the book. Yes? Yes. 2516297.4. Yeah, meters per second. So 25.2. Oh my God. 2.52 times 10 to the 7 meters per second. Okay, so that, and then that's the A part. The B part is the de Broglie wavelength. If you remember, it's wavelength equals h over p, which equals h over mv, which equals 2.89 times 10 to the minus 11 meters. Okay. A10. Ultraviolet light of wavelength 166.7 nanometers is shone onto a metal surface of work function we don't know. When the light comes in, an electron is released with a speed of 9.602 times 10 to the 5 meters per second. What is the work function? So we use the formula minus hf plus work function equals ke. So work function equals ke plus hf. So that's a half mv squared plus hf, which is c over lambda. So that equals plus h, which is 6, and then c, which is 28, over. Right, so when you hit all the numbers in on the calculator, you'll get 1.61 times 10 to the minus 18 joules. And then the last part is what's the threshold frequency, which is work function over h. Mass of the electron, yeah. Oh no, photons don't have a mass. – 2.43 times 10 to the 15 hertz. Yeah. Yeah. Right, so that's section A finished. Now on to section B.
So there's normally 5 sections.
Now there is, yeah. Yeah. A1. Definition of simple harmonic motion. That's in your notes. You know what that is.
Yeah.
It's the acceleration, or the force is proportional to displacement yes. From an origin. And second one, what is the amplitude? The amplitude is the maximum displacement. Okay, B. You have your spring of length 0.085, and then you stick a mass at the end of it, and it falls down a bit by a distance of 0.0. Oh, so the new length is now 0.121 meters. So that means the extension length is 0.36, is it? No. Yeah. Sorry, 0.036 meters is the extension. And the mass is 0.034 kilograms. So there's a force up and a force down, which are balanced. The down force is what? What's the down force? The weight. And the up force is from Hooke's law. So you have mg equals k delta x. So k equals mg over delta x. .265 newtons per meter. Next part is what is the it's pulled down, so it starts to vibrate like this, and they give us the amplitude of 0.015 meters. What's the time? Well, you know the formula. What is it? T equals 2 pi root. For the time? No. 0.38. Maybe you typed it in wrong. 0.034. 9.265.
I got K wrong.
Ah, well then. Maybe I got K wrong. Did you do it this way?
Please.
I can't find where I
Did you get the same answer for K, Andy? Yeah, okay. Right. Next part is for babies. What's the frequency? 1 over the time. 2.63 seconds. Maximum, this seems so familiar, like I did one just like it. Maximum velocity is a omega, which is a times 2 pi over t. What is what? A. Okay. What is the acceleration when its distance is that? So you have this other formula which I never remember. Oh no, not that formula. Sorry, this one. We have A equals minus omega squared x. I don't really care about the minus though, because it just is the direction. 2 pi over t squared x and the x is 0.012 meters per second squared. Well, this is all very straightforward.
Why is there
Hmm?
Why is there
In the question, that's the x. Okay, you have a pendulum. Oh, this one was a little tricky. So, what they have here is you have a pendulum with some length, and then you increase the length a little bit, and the time increases by 1/4 of a second. So they want to know basically what is the T and what is the L. Do you understand the question? Did you get an answer?
No.
How come? Too difficult, or Andy, did you get an answer for this? No. But do you understand what they're saying? Yeah. So when they increase the length, the time increases. But they don't tell you the length of the time. Yeah. So here you know that T equals 2 pi root L over G. And here you know that T plus 0.25 equals 2 pi root L over G. What would be the best way to solve these? What do you think? Yeah, but how? Messy, ugly. Yeah, but which way? Which way around? I think it's so ugly. I could get the L there, and I could get the L there. Oh, it's so ugly. Okay, that's fine, that's fine. You have to read that now?
Yes.
Oh, you're just going to leave me with him. Right, but just before you go, this is the last part of the question. So you can see that it's a maths problem where you have to find L and T. You can watch the video to see how I did that, okay? How long will you be? 20 minutes? What room?
B301.
B301. Who will do it? Connell or Dennis? Okay. Good luck. Good luck. Right, what do you think, Karen?
I think we should square the whole thing.
Oh, I really don't want to, but I think you're right. I really don't want to, but I think you're right. Okay, so I get T squared equals 4 pi squared L over G. So I have T squared, 4 pi... I have GT squared over 4 pi squared equals L. You're happy with that? Oh my goodness, I have to square here. Right, T squared plus twice the first by the second plus the second squared equals 4 pi squared over G L plus 0.301. So I think I should put the L in here. T squared plus a half T plus 0.125 equals 4 pi squared over G GT squared over 4 pi squared plus 0.301. So ugly. Oh, but that's nice. Look what happens here. Done. So they'll cancel when we multiply. So we'll get T squared plus 0.5T plus 0.125 equals T squared. And then when I multiply that here, I get plus 1.211. Oh look! Okay, maybe this isn't as bad as I thought, because now the t squares are cancelling. So I get 0.5t equals oh wait, hang on. This isn't hang on. I said this is 0.125 here when it's not. It should have been, sorry, 0.0625. So that needs to be changed as well. So that needs to be changed as well. Sorry about that. Okay. 1.1485. Right, so I got the T is 2.297 seconds. And if I put that in there, I can get the L. L is 1.311 meters. Right, that's B1. Now on to B2. Is that okay for you?
Yeah.
B2 is my favorite. Yay, Kirchhoff. So, what's the first one? Kirchhoff's first law. What one's that?
Is this the loop law?
I don't know, I never get the order right.
Law. I think it's the junction law, but then it's the loop law.
I think I would have thought the other way around. Go on, quick Google on your phone there.
The first is junction.
Right. So the junction law states that if you add up all the currents going into a junction, that the total is 0, and this is the conservation of charge. The second one is the loop law, which means if you add up all the voltages around a loop, you should get 0, and this is the conservation of energy. Ooh, look at this nice diagram we have now. Look at that. Right, are you ready to make some equations? Alright. Can I go down?
Yeah.
Right, let's do this thing. Right, so what loops do you feel like taking her in? I think we should start at the E maybe, yeah? So we have, do a small loop. E now hang on, do we minus or plus that for, we plus it. E plus 4 minus 6I1 minus 5I2 equals 0. Can you see my loop? Right, let's make another loop starting on the, going around the outside. E minus 12 plus 2 times 1.5 minus 5I2 equals 0. And then we'll also make a junction law. We'll say I up the top, I1 minus I2 minus 1.5 equals 0. I'm using the junction at the top. That's actually quite good because I can solve these two together by just minusing them. E minus E is gone. Yeah. 4 minus 12 is 16.
If they're going away, we minus. If they're going towards the junction, we plus.
Oh, it doesn't matter. You get the same answer. E minus E is gone. See here? 4 minus 12 is 16. Then we'll have... Oh, sorry, I should put these together, actually. So instead of 16, what I have is 4 minus 12 minus 3. So I'll have 13. these will cancel. I'll have 13 minus 6I1 equals 0. So I get I1 equals 13 over 6 amps. When I put that in there, I can get my I2. So I2 equals 23 over 2 amps. And when I put my I1 and my I2 both into the I2 into the second one, I can get E. So if I put that in here now, I can get my E, which will be 5 times I2 minus 3 plus 12. So my E is 133 over 2 volts. That's it. So I1 is 2.17 amps. I2 is 23 amps.
It was 33 over 2.
Where did my 2 go? Thanks. 23 over 2 amps. And then, sorry, I'm being silly. 11.5 amps. And then E is 133 divided by 2, 66.5 volts. Yeah. I don't think I made a mistake. The E seems very big to me, but whatever. What's the voltage between B and A in the diagram? It says B and A. Right, let's have a look. Yeah, so what's happening here, we have, basically they have this picture. This is 4 volts. And this here is 6 ohms. And which way is the current going? It's going to the right. So the current goes along chunk, 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 to the right. So the total voltage, so it's a bit weird, but this cell here is acting like a resistance because it's the wrong way. It won't be giving us 4 volts, it'll be taking 4 volts. So we'll lose 4 volts from the cell and we'll lose voltage from the resistor. V equals IR. So that'll be 6. Now what's the I1? What did we say the I1 was?
0. I mean, 13 over 6.
13 over 6? Was it?
Yeah.
Oh, nice. So then that's just 13 plus 4. 17 volts is the answer.
So you don't have to take consideration the other part, just that one line.
Well, they're just looking at from B to A. So yeah, just look at B to A. See, it's such a quick question when you get into doing it.
You have to understand it.
Well, that is true. Okay, can I continue? Yep. Right, we have another circuit diagram. What's the voltage output? So, what we basically have to do is simplify the circuit. We have here 12 volts to begin with. Then we have 2 resistors in parallel. And then we have another 2 resistors in parallel that connect to here. And then we have our voltage is coming out. That's such an ugly diagram. Let me at least make it a little bit more respectable. Oh, even worse. Right, and then we have our voltage coming out here. And the V is what we want to calculate. So first thing I'll do is I'll add those resistors together, yeah? What rule do I need to use?
1 over R.
Yeah. You don't need to see me do that, right? I can just... So, on the top we'll get a 4 ohm resistor, and then on the side here we'll get 1/8 plus 1/40. We'll get something. You get a 6.67 ohm resistor, and then here is 12 volts. But if you look very carefully, I can redraw this again like this. Now, do you know why maybe I did that? But there's another reason. This is a special type of circuit. Do you recognize it? Do you recognize it?
I mean, yeah, it looks maybe you can get the eye.
I wonder if it's in your formula book. No. It's a potential divider. We had a whole lesson called potential divider. It's when, never mind, you'll have to check that out now. You have an input voltage here and an output voltage here. And you have this formula, V out. No. And this is R1. This is R1 and this is R2. And you have here R1 plus R2. And I think here was R2 times V in. Oh, come on, you're breaking my head here. Do you? I don't know. So the answer is 7.5 volts. The next part is they want the power on the 20. So power equals IV. But the problem is we don't know the I, but we can change the I. The I is V over R, so it's V squared over R. Now, do we know the voltage on the 20? Well, the voltage on the 20, we can know it. If this voltage here is 7.5, then what must this voltage here be? Well, the total has to be 12, so it has to be 4.5. So the voltage is 4.5. So 4.5 squared over 20. (1.0125 watts). And lastly, what's the yeah? Only the 20, yeah.
Not the 20 ohm resistor plus the 5.
No, but I know that the voltage is the same for the 20 and the 5 because they're in parallel. Right, last part is how much charge flows through the 5. So the Q equals IT. Now we don't know the I, but we know it's V over R T. And it's 1 minute, so that's 60 V over R. And we know the R is 5, so that's 60 V over 5. So that's 12 V. So what's the voltage going through the 5? Well, that's the same as the one going through the 20, which was 4.5. So 4.5 times 12 is 54. 54 coulombs is the answer. And that's B2. Right, B3. Right, what's the nucleon number?
The number of protons plus neutrons. I mean plus nucleons.
No, plus neutrons, you're right. the radioactive isotope francium 221 contains 134 neutrons. So 221 minus 134, it has 87 protons. It releases an alpha particle and then becomes a different material called asthane. So if it was releasing an alpha particle, it's releasing a 4,2 helium, so then this would have to be 217 85. There we go, there's that one. That's easy to do, isn't it? Yeah. Now, we have to make the graph. So, what do we have here? Time in minutes. And next is activity in megabequals. Right, what's happening with the times? Are they going up in 2s each time?
If it's decay by emission, that means
It says alpha. You see, this annoys me in the exam. His alpha looks like an A, but that's by alpha emission. Yeah, other students thought that as well. But whatever font they're using for Greek letters, it's really bad. Just be careful about that one, okay? Right, the activity, what's the first one? 12.31. Is your exam clean? No, you're writing on it, are you?
I mean, it's quite clean.
Oh yeah, because I need to photocopy a clean one. I'll do that sometime. I lost my clean one. I might have scanned it in, I don't know.
Alright, look, there's a mosquito.
Yeah, no, that's me. I photocopied them into the, is he still, did you get photocopied in? Yeah, I photocopied them in. Oh well. Right, next we have to complete the table, so that's log activity in megabequals. This is very straightforward, isn't it? You're okay with this? Just get the logs and put them down, and then for the next one is the graph. What do we put on the x-axis?
The time.
And the y-axis?
The log A.
Yeah, so what title will we call this graph?
No, it's not log A, it's A. Sorry.
No, you were right the first time, log A.
Oh, oops, I missed the log. My bad.
Right, so the title is log activity against time, and the x-axis is time in minutes, and the y-axis is log activity in megabequals. Nice graph? Oh yeah, sure is. Insert the trend line with the equation. No need for a messy graph paper for me. What's the decay constant? So do you remember how to get the decay constant from the graph?
The slope.
It's the slope. So it's minus the slope, isn't it? Yeah. So it's the decay constant is 0.144. Part 1 is done, part 2 is done, part 3, decay constant is 0.144. What's the unit? Per minute. Because we're using minutes. What's the half-life? The half-life is log 2 over the decay constant. So that's 4.81 minutes. What's the activity after 20 minutes? So the activity is A0 E minus lambda T, which would be 12.31 megabequals is the unit for A. E minus 0.144 times 20. which is 0.69 megabequals. And lastly, what is the initial number? So you have A equals minus n lambda. So n is minus A over lambda. So really I should have activity as a negative, but we'll just drop the minus here. A0 is 12.31 and the lambda. Now, this is where you have to be very careful because activity is measured in megabequals and bequals is atoms per second. But what is my constant here in? Minutes, so we'll have to convert that into seconds.
And the other one's a mega. I mean mega.
Yeah, and it's mega. Now it's 0.144 per minute. If I just go to the side here, 0.144 per minute is equal to 0.144 over, and you see minute is 60 seconds. So it's 0.144 over 60 per second. So I just have to divide it by 60. And it becomes 0.0024 per second. So on the top, what you have is atoms per second, and on the bottom you now have per second. So they cancel and you're left with atoms. It's a big number. It's 5.13 times 10 to the 9 atoms. And that is B3.
But the A is,
Hmm?
the A is not 12.31.
It is, isn't it? At the beginning? It's the initial. B4. Continue? Yep, okay, B4. The planet Venus takes 224.7 days to orbit the Sun, and the radius is 1.082 times 10 to the 11 meters. What's the angular speed? So the first one, T equals 2 pi over omega, so omega is 2 pi over T, so that is in seconds. 3.236 times 10 to the minus 7 seconds. No, radians per second. Right, part 2, what is the linear speed? V equals omega or. So just multiply this by or. And that will be 35 kilometers per second. Part 3, what's the mass? So you have this formula for circular motion. F equals, now you can use Kepler as well, so you have a choice here. Do you want to use Kepler or do you want to use circular motion formulas? Okay, so you have F equals m omega squared or. So we can have m equals F over omega squared or. Now do we know the omega squared and the or? Or actually another one as well, you have the other formula mv squared over or. So you can have the m equals F or over v squared. No, I think this is too messy. I think it's much easier just to use Kepler. So Kepler said that T squared, let's see if I remember this, 4 pi squared, I don't remember, there's a G,
Big G somewhere.
can you look it up in your notes?
Maybe they got the phone.
Hang on, let me think, there's an R cubed in it, there's an M, it's 4, is this it? Don't remember. Yeah, type it in. Or do I have it upside down? I think it's upside down. I think it's like this. Wait, I know, Hareen. If we get the right answer for the mass of Venus, then we have the right formula. So, the mass equals 4 pi squared or cubed over gt squared.
The big M is the mass of
The planets we're looking at.
Venus.
Yeah. This seems too big. Oh, that's square rooted, thank goodness. What's the mass of Venus? Is it 2.74 times 10 to the 22 kilograms? Oh, sorry, that's the mass of the Sun. I've done something wrong here.
Mass of Venus is
No, that can't be the mass of the Sun. That's too small.
Venus is bigger.
No, I have the mass of Venus, that's okay. Sorry, you asked me what the M is for. The M is for the Sun. The Venus is going around the Sun. The M in the Kepler's formula is for the center. But this formula is wrong. Can we look it up? My mass of Sun is way too small. Yeah. Keep going. Well, maybe it's not second law. Sorry, it's third law. There we go. Oh no, that's not quite it. That's it. Right, so hang on. It's 4Q. Yeah, hang on. So the GM is under the 4 pi squared. And if I rearrange that, I have I have R cubed over T squared equals G. Yeah, okay, so then I just typed the numbers in wrong. It's the same, isn't it? Right, let's try this again. Square root 4 times pi squared times the radius cubed, and the radius is 1.082 times 10 to the power 11, and the g is 6.67 times 10 to the power of minus 11. Wait. Sorry. Excuse me, I'm being quite stupid. This is the formula, but I'm looking for the mass. So I should write m equals 4 pi squared or cubed over gt. And my t is 2 to 4.7 days. Thank you. It's a bad day. Right, this seems like the mass of the Sun, 1.99 times 10 to the 30 kilograms. Okay, next. The mass of Venus is that and the radius is that. What is the time taken in minutes for a satellite to complete one orbit? Okay, so again we can just use Kepler, except this time we do want the t. It's 4 pi squared or cubed over gm square root. 4 pi squared times the radius cubed and the mass of Venus is what's the radius of Venus, please? It says it in the question.
The radius is 1 point. Oh wait, the radius of the orbit or just the radius?
No, the radius of Venus.
6052 kilometers.
6052 kilometers. But the satellite is 200 kilometers above the surface, so I have to add on 200 kilometers. A.
Sophie and Grace and me, we did together.
The three of you?
Yeah, because today Sophie's partner didn't come to school.
Whose partner?
Yeah, Lydia didn't come to school.
Didn't she? Okay, so the three of you together.
Yeah, it's better.
It's better that way, is it?
Better than only me. Actually, me and Grace cannot understand one problem about section B. Part 3.
What's part?
Sophie can answer that, so we just follow her.
Good idea. 252 seconds. Right, next is the gravitational field strength, which is gm over r squared. Which is, oh wait, is it r squared for g? No, it's r squared, isn't it? No, I think it is.
Yeah.
Yeah. 8.86 newtons per kilogram. Okay, so Andy, we are on B4B. If you want to have a look. So we're on the B part now. Define electric field strength. That's in your notes. It's the force experienced by a charge in an electric field per unit charge. Congratulations. I heard the three of you were together.
Yes.
And it was a disaster. Andy, he was telling me. Andy was telling me the two of you were terrible.
No.
I trust you.
So you wouldn't stop talking, blah 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 blah.
No.
What were your topics? Computers, good.
Computers or the social life of people.
Okay, good.
For children.
For children, yes.
I read this question.
B4B2.
B4?
Yeah, we got a lot done without you here.
B4?
B4, yes.
What?
Yes.
Did you?
Yes, it's all recorded. I think so.
B4?
Yes. Yes, B4. It's much easier without Okay, can we continue? Right. Right. So what we have here is 4 charges. This is 2 microcoulombs. This is 4 microcoulombs. This is -3 microcoulombs. And this is 9 microcoulombs. And we are in the center, and we want to know what is the electric field strength at the center. So let's imagine we're in the center and we have a charge of Q.
So they're balancing direction.
No, it's not balanced. It's not balanced, so this Q will move somewhere. If you look at the picture, let's imagine Q is negative. Where would it move?
Towards the positive, towards the right corner, towards the bottom right.
Wait, guys, wait. B4, B2. Here's a picture for it. Yeah, before we get to that, though, imagine I put a positive charge in the middle. Sorry, a negative charge in the middle. Or no, actually a positive charge, yeah. If I put a positive charge in the middle, which way will it move?
Where did the motion origin?
I put a charge here, in the middle.
Why?
Well, because they want to know what is the electric field strength at the center. So imagine there was a charge here in the middle. Which way will it move? Towards D, shouldn't it? Because these will push it away, and this will pull it towards. So it should start to move this way. This is plus.
And this is minus.
Yeah, and these are pluses.
Okay.
Yeah? So what I want to know is, if I know the force here, then I can know the electric field strength. So I'm going to try and find the force here.
But how do you know it's the point in the middle is
B.
positive?
Oh no, well, no, that's, if you remember for electric field strength, the electric field is what way a positive charge would move. So if a positive charge starts moving this way, then we say the electric field is going that way. Yeah? So let's have a look. So here, if this is positive, it will be pulled to this, yes? But it'll be pushed away from the 9. What's wrong? This is confusing you, isn't it?
Push it away like this.
This is confusing you.
Even 9 is 9 nanocoulomb.
Microcoulomb.
Microcoulomb is stronger than 2 microcoulomb. So it pushes to the 2.
No, what I'm doing is I'm drawing the 4 forces. There's one force going this way, one force going this way from the 9, pushing it away. There's one force going this way, pushing away from the 2. And then there's one force going this way, pushing it away from the 4. Yeah, but there is another way to do it. Maybe I'll do it the other way. Because we have a formula. Does anybody remember the formula for electric field strength?
No.
K.
No, wait. Okay. I read the difference somewhere. E equals
Yeah, it's in the book.
1 over 4 pi.
E equals KQ over R squared. Here.
That's radial field.
Radial field means coming out like a circle. So this is the formula for electric field strength. Radial. Radial means coming out like a circle. And so this is the formula I'm going to use. There's an electric field from this one. Yes, this distance, this one, and this one. There's 4 fields. So I have to use this formula 4 times.
So this is plus, this is plus.
I'll draw it here. Yeah. Let's do this one at a time. Watch carefully. So the field at the 2, is the field going in or is it coming out?
Out.
Very good. So there's a field going out here, yeah? So in blue, there's a field coming out from the positive. How strong is that field? Well, I can just use this formula.
How do you know the radius?
We have to work it out. Now, can we work out the radius here? The or?
Use
Yeah, just use Pythagoras. Because we know this. How much is this?
0.5.
Yeah, and then this distance?
Half of 0.5.
Yeah, so we can get it from Pythagoras. So the or we can get from Pythagoras. It will be square root 0.5 squared plus 0.75 squared over 4. I got the or is 0.625.
We use the radial strength formula for the multiple ones.
No, because it's moving out like a circle. Radial
Then when do you use the other one?
in other situations. Right, what do I use for the Q, for the first one? What do I use for the Q? The charge. Here it is.
The charge
2.
yeah.
10 to the minus 6. Yeah. So this is 46016 newtons per coulomb.
What is the Q?
That's a constant, which is in your formula book.
The Q is just
The Q is 2 micro. K is in the book, I think. Here it is. Here's the K, here. K is 1 over 4 pi epsilon 0, 8.99 times to 9, yeah. It's not on the calculator.
It's not calculated.
460.
Is the answer.
It's the whole answer.
Whole answer, yeah.
But there is still K in fact.
No, it's a K.
Yeah.
But what is the whole answer? You have to do 4 times?
Yeah, I have to do it 4 times then.
But it's only 1 time.
I know. So I'm too doing it one by one. Right. Next, Harry, is I'll do this one. Yes? Now which way is this field going? It'll be going that way. Right, so then that's E1. So E2, the only difference is what?
The Q.
The Q is bigger, isn't it? So the answer you get here will be 92033 newtons per coulomb. And then with E3, you get 69024 newtons per coulomb. Sorry, that's actually E4. I'll do 1, 2, 3, 4. Okay, so E3 will be the biggest one. It'll be 207,073 newtons per coulomb. Okay?
We have to
Not finished yet.
No, 4.
Yeah.
But this coming back.
Yeah, it's the other way then. So going to draw the fields now in different colours.
So the 4 is minus 3.
We don't put a minus in field strength, we just change the direction. Yeah, so I'm going to draw it now.
Why are you scared?
So there's a square here. Yeah. It's the radius, it's this distance. Yeah. Okay. Can I draw it now? So let's draw it here. I'll try and make it nice and big and clear. So let's say we have 1 coulomb in the middle. The E1, if we go back to the picture, we said the field is going to the right, bottom right, the E1. So if we have 1 coulomb, how much force is pushing it to the bottom right? If it's 1 coulomb, yeah. Well, I gave you the strength. The strength was, where's it gone? It was 46,016 newtons per coulomb. So if you had 1 coulomb, how much force would you have? Well, it'd be 46,016 newtons, wouldn't it? Yeah. Now the second field, I'll do it in blue. Which way will that point?
Towards from the top right to the top left.
This is newtons per coulomb, okay? From which way? To the bottom left. Right, okay. How much is that one? 92033 newtons per coulomb. Let me just get rid of this. It doesn't have to be 1 coulomb, just forget about it. This is the field. Okay, the next one, E3, the third one. Which way is that pointing? Top, up and left?
Yeah.
Yeah, up left. How much? 207. Yeah. 73 newtons per coulomb. And the last one?
69.
Which way though?
Okay, so.
Yeah, so I'll do that in green. How much is that one?
69024.
Now you see what happens here when you combine these 4 fields. The blue field and the green field, what happens to them? They come together to make a stronger field. So in this picture here, they're going this way with 92033. Hey Roland, are you in here?
I'm supposed to, but maybe
Possibly the...
Here's the one.
no, not that long. There might have been a room change with Connell.
Okay.
Maybe. Yeah.
Okay.
Thanks. 92033 plus 69024. That's 161057. Oh wait, hang on. I'm not sure if I'm here till 1 or till 12. Oh no, I believe that. You have 1 hour here, isn't it? You give me 5 minutes to wrap up the question and difficult here. Yeah, thanks. Okay, so that's that many newtons per coulomb. And then what happens here on the diagonal?
It minuses.
This one takes away from this one, so we just have this many here. 207,073 minus 46016. So that's 161057. This one minus this one. This one minus this one. Yeah, because they're opposite directions. Is it the same number? 161057, this minus this.
No, I mean the top and the bottom is the same.
What are you talking about? This
No,
number
I
is...
mean, okay, move down. Okay, see.
Oh yeah, that's a good thing.
Yeah, then we just move to the left, right?
So then, to finish it, what we have to do is this has a component this way and this way, yes? We're going to put it, resolve it x and y. So this has an x, this has a y, and then when you look here, Hareen, this has an x and it has a y. But what happens with the x and y's? They cancel. So you're just left with a component going to the left. The field goes to the left. So the answer will be 2 times 161057 times cos theta. And we have to work out the theta here, which will be tan inverse opposite, which is 0.7992. That theta is 36.9 degrees. Hold on. 257,691 newtons per coulomb left. That's the final answer. How can I get the theta? Easy. I have the triangle. I know we know the horizontal and the vertical in the picture. We can easily get the theta because we can draw the triangle. Yeah. This is a very difficult question. Most students don't like it in the exam and they don't do it. But I know everybody hates fields. Okay, great news. We only have one question left. We'll do that tomorrow and we'll finish the maths exam tomorrow in the double class in the morning. Please remember to bring the maths and physics exam. Alright, get out of here.